Hello everyone, this is Sayedeh Leila Noorbakhsh from Illinois Institute of Technology. Today I want to present our work titled as Inf2Guard, an Information-Theoretic Framework for Learning Privacy-Preserving Representation Against Inference Attack. This is joint work with my teammate Binghui Zhang, my advisor Binghui Wang, and our collaborator Yuan from University of Connecticut. All of us know that these days machine learning is like electricity to many technologies, and because it is very useful, many service providers like Google, Microsoft, Amazon, and many others give us training API that you can easily upload your data to the cloud and use the prediction API. But when we look closely to this framework, could we ask this question that is it possible that this framework or in general machine learning can leak sensitive information from training data or not? In our paper, we studied three most well-known attacks: membership inference attack, property inference attack, and data reconstruction attack. In membership inference attack, the attacker aims to infer whether the particular data is in the training data or not. And we can see the consequence of membership inference attack, for example, in healthcare data, where attacker can infer about the membership of the data and then can leak the sensitive information of the patients. In property inference attack, the attacker aims to infer about the statistical properties of the training data. For example, you are training a machine learning model, and attacker wants to infer about what was the female ratio of the subset of the data that you are training, which is completely different from your primary task. We can see the effect of property inference attack, for example, in consumer behavior analysis, when attacker can get the information from aggregation from the training set. In data reconstruction, attacker aims to reconstruct the original data from the encoded feature. Data reconstruction attack can occur in facial recognition systems that attacker can reconstruct the original data and use that or construct the data for its own purposes. When we study this attack, we want to ask this question: that can we design a unified privacy protection framework against these inference attack, membership inference attack, property inference attack, and data reconstruction attack, and also could we maintain utility at the same time? And another question is that under the framework, can we further theoretically understand the privacy and utility trade-off of the privacy leakage against the inference attacks? Okay, let's first introduce our threat model and then introduce our defense. In our threat model, we have three main roles. The first and the core part of that is defender, or named as a data owner or trusted service provider. The defender try to learn the shared data representation in such a way that are resistant to these inference attacks that I mentioned. And we have task learner or data owner that his objective is to develop an accurate classification model for our specific machine learning training. And obviously, we have an attacker that seeks to extract the sensitive data from our representation learning. And here, attacker knows about data distribution, but doesn't have access to the intermediate level, for example, the model parameter or model type. In our defense, we are inspired by information theory and design a customized mutual information objective for each inference attack. And this is a good news that we have one objective function and we can generalize it into these three kinds of attacks that we have. We have two main goals. The first one is privacy protection and the second one is utility preserving. Let's see what is mutual information. Mutual information measures the amounts of information that one random variable gives us about another random variable. And actually, mutual information quantifies the reduction in uncertainty about one random variable due to the knowledge of another random variable. And this is the mathematical expression of mutual information, and we have seen the applications of mutual information in real world, like feature selection, clustering, and the most important part is privacy preserving mechanism and inference attack defenses that we use in our defense. Okay, because the time is limited, I only focus on membership inference attack, but you can reach out to the paper to see the detail about property inference attack and also data reconstruction attack. There are lots of defense for membership inference attack, but most of them have two key limitations. First group do not consider about the utility. For example, DPSGD or DP encoder decrease the utility too much. And the second group doesn't have privacy guarantee, right? Adversarial regularization or USENIX. In our defense, we wanted to formulate our two main goals with mutual information. The first one, we want that our shared data representation have at least information as possible about our private attributes. So when we have our data representation and attacker wants to infer whether this is the member or non-member of the training data set, the attacker cannot distinguish between member and non-member and is like random guessing. He cannot distinguish anything. And the second goal is that we want that our shared data representation have the most information as possible about the label of the data that we are training. And you might know that solving these two mutual information is very challenging because calculating MI between arbitrary variables is infeasible. So how we can address this issue? We are inspired by MI neural estimation that transfer the untraceable MI calculation to the traceable variational MI bonds. And the good thing is that we are capable of parameterizing each bond with a deep neural network. And obviously, with having deep neural network, we can train the neural network to approximate the true MI and learn representation against the inference attacks. Okay, in this slide, I want to satisfy the first goal that we have, that we want to minimize the amount of information between our shared data representation and the private attribute that we have. We use the upper bound of the mutual information called variational club upper bound, and in the formulation you can see that we have auxiliary distribution named as Q5. And Q5 is responsible to estimate the probability distribution of our private attribute given by shared data representation. And the process leads by a min-max objective function, as you can hear. Yeah, and we can interpret the min-max objective function at adversarial game between the Q5 and our shared data representation, or here encoder F. And in this slide, we want to formalize our second goal, and we wanted to maximize the amount of information between our shared data representation and the label of the data. So here again, we see auxiliary distribution here, Q omega, that is responsible to predict the true label of the training data given by the non-private attributes that we have. For here we have U equal to 1 means the member of the training data. So again, the process leads by max here objective function, and we can interpret it as cooperative gain between the encoder and Q omega. And by combining these two objective functions that we have, we will reach to the final objective function, and we have a lambda parameter, which is a trade-off between privacy and utility. So as I mentioned, by solving this objective function, we have three parameterized neural network, encoder F, membership protection network G5, and utility preserving H omega. Let's see how we implement our method and defense on machine learning and deep neural network. Obviously, the first part is that we train our encoder with utility network, and after that we freeze the encoder, and in this part attacker can infer about that whether this particular data was in the training set or not. And here attacker can easily infer about about the membership and non-membership of the data, and for CFAR10 we can see that is reach up to 70%, which is pretty high. And after that, we apply our defense to the pre-trained encoder, attacker, and utility, and we see that attacker cannot anymore distinguish between members and non-members, and utility is still very good, have still very good accuracy. We applied our defense here. And because time is limited, I don't want to go deep to theoretical result, but you can reach out to the paper to see the privacy leakage bound actually for theoretical result and actually utility privacy trade-off. And you can, there are lots of mathematical expression that you can see in the appendix of the paper. I don't want to go through it. And let's see the experimental result for membership inference attack. In the first table, you can see the impact of lambda, the differential, the parameters for utility privacy trade-off. As you can see, the utility from 0 to 0.75 only decreased 1%, which is pretty good. And the membership inference attack start from 70% 20% up to 51% is like random guessing, and it means we decrease the attacker accuracy too much, which is pretty good again. And on the other hand, we see our result on the Leila attack, which is a very strong attack for membership inference attack, and we see the true positive rates versus false positive rates, and the result on our Inf2Guard defense. And this is TSNE embedding result on the learned representation on CFAR100 before attack and after attack. You can see that we can easily distinguish between the classes for utility, but for membership inference attack, the attacker cannot distinguish between two of them because it's like random guessing. It's 50 to 50. 70 to 51. And now we want to see the the experimental result for property inference attack. We compare our method Inf2Guard with DP encoder. We set the PI property inference accuracy up to 34%, and you can see the difference between the utility accuracy. And the second part is for, again, TSNE embedding result on property inference attack, as you can see again. And this is the experimental part for data reconstruction attack. Here we set the utility up to 78%, and when we apply our defense to the data representation, the attacker cannot reconstruct the data. As you can see, when the utility is fixed, the privacy on our defense is much higher than, for example, DP or without defense. And another result is for CFAR100, again the same thing, but attacker cannot reconstruct the original image from the shared data representation. Conclusion, in our defense, we could design a unified information-theoretical framework for running privacy-preserving representation for membership inference attack, property inference attack, and data reconstruction attack. And in our paper, we have guaranteed privacy leakage. We guarantee the utility privacy trade-off, and also we design a state-of-art of the utility privacy trade-off. And you can contact me or my collaborator. This is the QR code for the code and paper, and big thanks to our supporter, NFS and Cisco, for their generous support. Thank you so much for your attention.